This is the Deep Space Network. 3 massive antenna stations strategically placed around Earth. They talk to spacecraft billions of kilometers away. 3 locations perfectly positioned: California, Spain, Australia. As Earth rotates, at least one station can always see deep space. Each antenna is 70 meters across. That's 230 feet. These are some of the largest antennas on Earth. Inside the control rooms, engineers monitor dozens of spacecraft simultaneously. Mars rovers, Voyager probes, DSN tracks spacecraft at every distance, from the International Space Station to the Moon, Mars, Jupiter. Multiple antennas can work together, combining their power, making signals even stronger, working as one giant antenna. So that's the Deep Space Network, tracking dozens of spacecraft. But how does this incredible technology actually work? Each antenna dish has thousands of precision panels, every panel perfectly aligned, accurate to millimeters. These antennas can track a spacecraft, moving at thousands of kilometers per hour, accurate to 0.001 degrees. The dish collects weak signal and focuses all that energy to one point, then amplified thousands of times. Every photon counts. The receivers are cooled to near absolute zero. Ultra-cold reduces noise, makes them incredibly sensitive. Sometimes all 3 stations track the same spacecraft together, combining their signals, making it even stronger and clearer. These antennas don't just listen, they also transmit, sending commands to spacecraft billions of kilometers away. Two-way communication. So that's how these incredible 70-meter antennas work. But now let me tell you about their most amazing achievement. Voyager 1 launched in 1977, visited Jupiter, Saturn, Uranus, Neptune, then kept going, still sending signals back. Voyager is now 24 billion kilometers from Earth. That's 160 times the distance from Earth to the Sun. A signal from Earth takes 22 hours to reach Voyager. Even traveling at light speed still takes almost a full day. Then Voyager sends its response back. Another 22 hours return journey, almost 2 days for a simple question and answer. Caught by the massive antenna, we successfully communicated with something 24 billion kilometers away. Amazing. Voyager sends back incredible data. Cosmic ray measurements, magnetic fields, temperature, particle density. After 47 years, still talking to Voyager. But here's the crazy part. How weak is that signal? Let me show you. Voyager's transmitter is only 23 watts, less powerful than a simple household light bulb, and we still receive it. As the signal travel spreads out in all directions, gets weaker and weaker. 0.00, many zeros, 1 watt, nearly nothing. That's why the antennas are so massive. 70 meters wide, every photon counts. The bigger the dish, the more signal collected. Then massive amplification, each stage multiplying the signal, amplified until it's strong enough to process. Without this, impossible. But the signal is buried in noise. Radio noise from space. Advanced computer filter out all the noise, extract the pure signal. Think about this, a light bulb's power traveling 24 billion kilometers, and we still receive it, decode it, understand it. So Voyager's signal is weaker than a light bulb, yet crosses 24 billion kilometers. But what about closer missions, like Mars? Mars is much closer, about 225 million kilometers average. Signals take only 12 to 13 minutes. Meet Perseverance, NASA's latest Mars rover. The Deep Space Network sends it commands every day. Engineers send commands from mission control. The signal travels 12 minutes to Mars. The rover receives it, executes the command, sends confirmation back. But 12-minute delay means rovers can't be controlled in real time. They need autonoms, onboard AI. The rover thinks for itself. Every day, the rover sends thousands of images, high-resolution photos and videos, gigabytes of information, all through the Deep Space Network. But there are multiple missions at Mars, Rovers all need antenna time. DSN coordinates everything, switching between missions. So Mars is relatively close, nearly real time, multiple missions coordinated daily. Even more distant missions? Let me show you. Future missions will go even farther. Proxima Centauri is 4.2 light-years away. Communication becomes even more challenging. The Deep Space Network is being upgraded. Even larger antennas, arrays of antennas working together, more sensitive. Future communication might use lasers instead of radio, focused beams. Energy doesn't spread out, stays stronger over vast distances. At light-years distance, spacecraft need advanced AI making decisions independently, fully autonomous exploration. One idea: relay stations. Spacecraft talks to nearest relay. Signal hops relay to relay, eventually reaches Earth. Breakthrough Starshot is a real project. Thousands of tiny spacecraft, propelled by lasers, 20% light speed. The future of deep space communication. Larger antennas, AI autonomous spacecraft. Real missions being planned. So that's the Deep Space Network. 3 stations around Earth, 70-meter antennas, talking to spacecraft at every distance. 60 years of operation, 24 billion kilometers, signals weaker than light bulbs, Mars missions daily, future interstellar travel. This is real. This is happening. Hit like, subscribe for more incredible space technology stories.